Hello, everyone. Welcome to this webinar. This is the Geotech 101 series, webinar 12 by the Young Professionals Committee of the Canadian Geotechnical Society. My name is Leonardo. I am a graduate student at Western University in London, Ontario. Thank you, everyone who came today for this webinar. I would like to take a moment to advertise our Young Professional Conference happening in September in Manitoba. The registration has been extended. I'm going to type the link in the chat so you guys can check this out. Some housekeeping items. If you have questions, please enter them in the Q&A field. And if we have time at the end, our speaker is going to answer some of these questions. Please feel also free to join our LinkedIn group called CGS Young Professionals Committee to keep up to date. And with that, it's my pleasure to introduce our speaker for this webinar. Masoud is a geostructural engineer at Hatch with extensive experience in various aspects of geotechnical and tunnel engineering. His work spans a diverse array of civil engineering projects across a variety of soils and rock types, with a primary focus on tunneling, underground caverns, major bridge foundations, deep excavations, subsurface risk management, including preparation of geotechnical baseline reports and advanced numerical modeling. He has led geostructural design and geotechnical engineering for some of Canada's most significant infrastructure projects, including the Eglinton Crosstown Light Rail Transit in Toronto, Gordie Howe International Bridge in Windsor, Detroit, Ontario Line Subway in Toronto, and Confederation Line in Ottawa. His experience also extends to geotechnical design for a variety of other projects, including railway and highway embankments, retaining structures, slope stabilization, utilities, water and wastewater treatment facilities, and telecommunication towers. Moreover, he contributes to technical committees preparing standards, including the Canadian Highway Bridge Design Code, new Ontario Provincial Standards for Drilled Pies, and CSA S7, Pedestrian Cycling and Multi-Use Bridge Design Guideline. He has served as the chair of the Canadian Geotechnical Society's Southern Ontario section, executive member of the same section, executive member of the Tunneling Association of Canada, Ontario chapter, and chair of Geo Niagara 2021, the 74th Canadian Geotechnical Conference. He is currently the regional director of the Canadian Geotechnical Society. Please join me in welcoming Masoud Manzari.
Thank you, Leonardo, for the introduction. Hello, everyone, and thank you for attending. And many thanks to a Young Professional Committee of the CGS for organizing this event and allowing me to just share the last several years of experience with my colleagues. Given that there is going to be a long presentation, I just going to jump on it. Let me share my screen. And I'm going to turn off the camera. Okay. Leonardo, is everything look good?
Yes, everything is good on our end.
Okay,
Perfect.
thank you. Okay, as I mentioned, the main goal of this presentation is just sharing some of the experience I gained. Most of these projects, we have to advance the state of design, answer questions that we didn't have answers before, or we couldn't find a straightforward answers to. And is the result of collaboration between me and my colleagues and lots of hard work with lots of people. Therefore, I'm just summarizing a group of people's working here. First, we talk about the shaft resistance and the tool resistance of the cast in place concrete piles, because they are practically the dominant type of foundations for the large bridges. We talk about construction consideration as it pertains to the design and interpretation and use of pile load tests. A few pitfalls that some people may miss in the design or interpretation of the design. And to make the presentation interesting, we try to use examples of a couple of projects. First projects that we're gonna use, it's Gordie Howe International Bridge. That's the longest cable-stayed bridge in North America. It is practically 2.5 kilometers long from end to end. The clear span is 853 meters long. I have no pure water, as you can see in here, and there is one approach on each side of the crossing. It connects Canada in Windsor to US at Detroit. The subsurface condition, it's practically consists of man-made fill. This is one example on the Canadian side, and then very soft to very stiff, but predominantly very soft to firm clay, shown by green in here, and there, which is extend all the way to 20 to 21 to 25 meter depth. And there is 1 or 2 meter thick of hard pan. In this case, the hard pan is compact sand. In some areas, what silty clay, till, and then it's all underlain by the limestone bedrock. Here is a sample of a tip resistance of the piezo cone. As you can see, it's the clay. It's generally very soft to firm. The bridge has 2 main towers. Each tower is 220 meters high. That each tower has 2 legs, and each leg has 1 pile cap, and the pile cap supported by 6 piles. These are casting placed drill piles. On the Canadian side, there are 3.16 meter diameter in soil and 3 meter in rock. And on the US side, 2.92 meter in soil and 2.8 meter in rock. All of these are just based on the availability of contractors' tools, because the contractor on the US side and the Canadian side were 2 different companies. It all was designed by myself, but minor detail changes is not a design related issue, it's a construction practicality situation. Now, the piles are about 36 meters long, and if you recall, as I mentioned, is about 30 meters of it, it's practically overburdened with mostly fill and soft clay. The rock socket on the Canadian side is 4.5 meters long, and on the US side is 7 meters long, which we're gonna get there in the future why it happened. And the design bearing capacity of each pile is 216 meganewton factored in compression and 7 meganewton factored in tension. And the design was done that all the resistance, whether in compression or tension, is coming from the rock socket, not the soil. The soil provide lateral resistance. To provide you with some idea about what does it take to construct large diameter piles like this, I'm going to quickly go through a few pictures of the construction stage just to get a feel for it. Here you can see the height of the steel casing, which was used because we have artesian water, and we needed to make sure that the fluid inside stay above the groundwater level, which means it has to be higher than the artesian. That's the scale of the steel cage. This one is about for the pilot test. You may see the OSEL test in here, which we're gonna get there. These are one of the actual construction, whatever required for a slurry and a slurry recirculation. That's what it takes to place the concrete inside this. Here is a few piles during excavation completed, and this one is completed and cured. That's the overview of the pile caps, and all pile caps almost completed. Now we're going to have some discussion about the shaft resistance. Can you rely on shaft resistance for cast in place drill piles? This question may sound ridiculous for some people, and they say, of course we can rely on it. But believe me, I had enough conversation with enough people that they genuinely believe you cannot rely on shaft resistance for cast in place drill pile in soil, because they believe that the drilling would cause a stress release and therefore you cannot rely on shaft friction for the drill piles. This is not a correct statement, and I can see where people coming from. I show a couple of examples about how things could go wrong, but you can easily rely on the shaft friction. Shaft friction is sensitive or very sensitive to construction means and method in compared with the toe resistance. But in general, for equivalent load resistance between the toe resistance and shaft friction, you get less settlement, and it is less sensitive to imperfection of the bedrock below the toe. And lateral shaft resistance, providing lateral resistance for cast in place piles. Yes, it is correct that the drilling would cause a stress release and cause elastic relaxation. And the key point in here is elastic relaxation. But all of that get compensated by the pressure of concrete. For a couple of projects, we installed pressure cells inside the steel cage. And this graph is practically show whatever the pressure cell recorded. This high pressure in here is practically when the steel cage was installed inside the drill shaft. This is hydrostatic pressure of water or slurry at that height. And after a few hours, the concrete placement starts and the pressure increases. And if you look at the angle of this pressure increase, is very consistent with concrete having a full fluid behavior. Therefore, when you place the concrete apply a horizontal stress equivalent with a fluid with a density of 24 kilonewton per cubic meter. And that is even more than any horizontal stress that was already in the soil. It completely recovered the stress release. In this case, as you can see, by the time the concrete placement is finished and the concrete starts curing, you get some reduction in the stress due to the shrinkage. And another point to convey in here is this liquid behavior lasted for many, many hours, which we're going to get what that means in the next slide. But as long as the construction means and method does not disturb the soil, meaning change the soil metrics, and we only have elastic relaxation, the pressure of concrete recover all the stress release, and you're going to have full shaft friction. What is important is you don't disturb the soil, and also your concrete has the right workability. Plus, the concrete has the right workability retention, meaning the concrete at the bottom is still fluid by the time you finish placing all the concrete at the top. That's very important. And I'm going to show you an extreme case of the lack of workability or workability retention is if the concrete is not workable enough to pass through the cage. This is an example. You don't have any shaft friction. Therefore, yes, you can rely on the shaft friction, but that's subject to proper construction means and method. Shaft resistant in soil and rock. When it comes to the shaft resistant in soil, permanent casing, even if it doesn't have overcut, it still lead to lower axial shaft resistance. And one reason is you don't get the recovery of the stress from the concrete. Here is one example. We had the pile load test in the project. These values are the actual shaft resistance within the soil when we have the steel casing, even without any overcut. And these two are two conventional methods to establish the shaft friction in the similar soil with the same geotechnical properties. As you can see, the steel casing, the permanent steel casing has reduced the shaft friction considerably. And then using a permanent steel casing with overcut, it's an absolute no-no because it completely ruins your shaft friction and it softens your lateral behavior. Now, when it comes to the shaft friction, something that affects the after everything else is taken care of, meaning the workability and everything else. Another item that affects the shaft friction and ties to the construction means and method is the roughness of the drill shaft, meaning rougher the drill shaft, the sidewalls, higher shaft friction you get. This is shown in here. both theoretical, which is this equation, and actual test, and it showed itself as piles having this identical roughness versus having different diameter. What does this translate is the shaft reduction, ultimate shaft friction reduces as the diameter increases, assuming the same roughness. And here is the ratio between the production shaft to the test shaft. And as you can see, when is less than 1, as the test shaft to production shaft diameter is less than 1, um, the roughness of the drill shaft, the effect of the roughness in the drill shaft in the bedrock is less. Is more than the effect on soil. I'm gonna use another project. These beautiful bridges are part of the Portland project in Toronto. There was 4 bridges constructed with 3 different contractors. Therefore, we have one pilot test for this bridge done by one contractor, another pilot test at this location to cover 2 bridges, and another pilot test for a different contractors for a different bridge. And I got the result of a pilot test for a different project from a friend. And we're going to compare this in here. Therefore, we have 4 pilot tests. These 3 that I was involved are done by 3 different contractors, 3 different equipments. I can tell you even 3 different tooling to drill the holes, but they all has been constructed with the restrict specification. Therefore, everything you can say was done properly. And as you can see, the pilot tests are 500 meters from each other. For these 3 that the construction was very consistent, the ultimate shaft friction is almost identical for all practical purposes. Um, the UCS is very close for these 3 locations. For the 4th project, the UCS is less, and we get even slightly farther less ultimate shaft friction in here. This might have something to do with the construction means and method effect. Therefore, the shaft friction is tied to the means and method a lot, to the tooling, to the roughness, the workability, and all come to the effect. Now, during the investigation phase for some of these projects, we actually start developing a test, as far as we know, for the first time, and that was the test to study the friction and the resistance between the concrete and the rock. In this test, we took a rock core, cut it in half, therefore in vertical line, cast concrete on it, and then start putting this sample in a direct shear test, like that, and start shearing it to get us some idea about the ultimate friction between the rock concrete interface. And the idea is when you do the saw cut, that's almost the lower band of roughness you get in your rock socket. During the actual construction, we expect to have higher roughness. Here is the result for Gordie Howe project. The result on the right are on the Canadian side, the left on the US side. You can see the green lines are for when the concrete achieved around 32 MPa. And the black line is when the concrete it's around 24 MPa. To be comparable, on the Canadian side, it was 24. On the US side, it was 18 to 24. A couple of things to point. As the concrete strain increases, the shaft, the rock concrete interface increases, but the difference in the increase become less and less, and practically plateau where you reach the UCS of the bedrock. And then in the Canadian side, for this particular project, you can see the results are higher than the US side. Despite that, on the geotechnical point of view, these 2 rocks are almost identical. And the interesting result was on the US side, the concrete was more, sorry, the rock was more oily, natural. Therefore, we had more hydrocarbons in this limestone, We could even smell it on the US side versus the Canadian side. And as a result, everything else being equal, we get less shaft friction in this one. The test that I mentioned was done, and also the residual state. As you can see, again, there is a big difference between the post-peak to the Canadian side and the US side. And then between post-peak and residual, there is 2 to 3 degree reduction in the friction. We use all of that in establishing your design. And I'm gonna get there when how it compared with the actual results. Now, on the tool resistance, again, I heard some of my colleagues in the past, they said you cannot rely on the tool resistance. Why? Because they say in the sandy soil, you disturb the soil, you get almost no resistance at the toe. Or some people are worried that you can verify the cleaning at the base, therefore you can rely on the toe resistance. And I think most of the people, they think from the age that we send inspector inside the drill shaft to inspect the base, that doesn't happen anymore. However, we have very reliable tools to check the cleaning. Therefore, you can rely on the shaft friction. So you can rely on the toe resistance. The toe resistance provide more UCL resistance in compared with the shaft friction for everything is being equal. But at the same time, for the same similar load level, provide more settlement, therefore has a softer behavior. And it also is less sensitive to the construction means and method when it comes to the ultimate capacity, but it still is sensitive when it comes to the serviceability limited state. And it's tricky to understand or establish it when it comes to the condition of the bedrock below the toe, whether it comes as a kind of the fractures, voids, or hard seams. We get to one example in here. This is the same Portland project with that additional project when we had 4 pilot tests. You can see in here that below the tip, the rocks are very comparable. They have very close RQD. They have very close UCS. Even when it came to the shaft, there was more difference between them. If you recall, this was 10, but now below the tip of the shaft, they're very close. And the unit end bearing is very variable, understanding something. Some of these, they never achieve failure. They just max out to the capacity of the test. Some achieve failure. Some max out, but they close to failure. Therefore, you can call it that's the real failure stress at the toe. And this one didn't achieve failure. And still between even these two, the values are very different. And when you look at their settlement at 50% of the failure, you can see that the results are closer to each other, but not for this one. And the N factor, it's actually a ratio of 2. Some of this is contributed to the variation of the rock below the base. In this case, this is a shale formation with a limestone seam. In one of these, actually, when you look at the borehole log for the test shaft, you could see there's a 150 millimeter or a thick limestone seam a couple of feet below the toe, which could have affected the results. For Gordia project, we had lots of tests, lots of UCS testing, lots of triaxial testing, that the data were processed together. We even tested directional tests on the natural joint. Every single UCS test were analyzed for the style or the type of failure, because each failure can tell you a story about the rock behavior. And we even conducted a numerical simulation of the rock socket. Again, this is not what you do in typical day-to-day bridge work, but for a large bridge like that, it was warranted. The one in the left is the simulation of tension strength, and the right is a compression. And if you recall, I said the design was 216 meganewton factor for compression, 7 meganewton factor for tension, more than that. And a story to share with the team was one of the agency or entity were reviewing the work. provide comment that these compression results are excessively high. They send us a list of their project in US that the design ULS value was not even remotely close to this. And they were kind of telling us very politely that we are crazy. But we were confident on the result, and we went to the next phase of the project to conduct the pilot test. We did two pilot tests, one on the Canadian side and one on the US side. Why? Because we have two different contractors. Therefore, as I said, the performance of the drill pile depend on the contractor's means and method and quality. Therefore, we had to do two. And we had some changes in the bedrock. As I said, in one of them was oily. The rest of the properties was identical. The tests were planned to apply a total of 320 meganewton, 160 upward and downward. At the time, it was the largest pilot test in North America. It may still be the largest one. I don't know anymore. And it included 24 hours creep test. The tests were done successfully. We achieved the maximum load of the jacks in the O cell, and there was no sign of failure. As you can see, the right is in the Canadian side, the left is in the US side. Here is the mobilized shaft friction at the different part of the rock socket. You can see that on the Canadian side, it didn't even get close to the failure, around 4,500 kilopascal. On the US side is almost failing and is also moving more. And to refresh your memory, if you recall, when we did the test on the concrete rock interface in the lab, there is a good consistency on a couple of things. One of them was the behavior on the US side was softer, less ultimate capacity, shaft friction, was very consistent with this result. At the end, all of the design assumption was verified and proven to be correct. There are other aspects of the design for this type of bridges. I'm gonna go with one example. If you look at this photo, it provides the unfortunate. It reminds me, at least, for the unfortunate events last year in Baltimore, when the ship hit the pier and the bridge collapsed. Of course, in Gordie Howe, we didn't have any pier in water, but as you can see, the piers are very close. They're almost like 10, 15 meter behind the water line, and a ship like that hitting there, it's gonna impose some load. This is not the type of analysis that the conventional structural software are capable to do. If the pier was at the middle of the river, yes, the structural engineer could handle that easily, but now we had to step in and help the structural team working together. We end up analyzing and providing as full soil structure interaction models, apply the ship impact, and analyze the deformation and the load applied to the piles due to the ship impact, and provide them to the structural engineer, which they can use it in the design. The previous slide for the Canadian side, this is for the US side. Now we talk a little bit about construction consideration for the design. We talked about workability and workability retention. I'm just repeating it because it's very important. If you don't have proper concrete workability and workability retention, your shaft friction will be jeopardized. And on the structural side, your durability is gone. Here is another example for a project in soil. This project involved 3 pilot tests, all with 1.2 meter diameter. The pilot tests are 7 meter away from each other in a triangular pattern. They were done by the same contractor. 2 pilot tests were done by the same crew, and they all used the same construction methodology, which was dry drilling method or plug drilling method, I call, and we're going to talk about it a little bit in the next slides. And as you can see, the ultimate shaft is from 11 to 61 at this zone, 10 and 11 in here, or at this zone ranges from 91 to 161. And all of these variation has nothing to do with the soil property. They're only 7 meters apart. This huge variation is for the improper construction means and method, whether it was the side effect of the dry drilling method we can get there, or the bad quality of concrete or concrete workability. Uh, that's the side effect of improper construction means and method on the shaft friction. Now about the toe resistance. In Gordie Howe, we use a squid test. A squid test just give you a very high level introduction. It is an equipment that involves 3 probes. Each probe has a has a measurement in here, like a piezo cone measurement that measures force and displacement. They're very sensitive. They're being pushed at the base of the shaft, and they tell you how much sediment you have. Now, using the conventional values for identifying the sediments in the industry, even the one that are are introduced by the manufacturer of the squid test, uh, here is the result of the sediments. On the Canadian side and US side, that's the minimum 1.5 millimeter, 3.3 millimeter, maximum sediment 18 and 20, average 7 versus 10. Readings less than half an inch or 13 millimeter is 91%, 73%. This implies that the Canadian shaft was slightly cleaner than the US shaft. Um, but in reality, we got something very different. On the Canadian side, when we got to the maximum load, we have less than 5 millimeter settlement at the base plate. On the US side, we have almost 25 millimeter at the base plate. Very different. And if you recall, I said these rocks were identical on both sides, the rock mass even, not just the intact rock. The only thing was different on the US side was a little bit more oily, more hydrocarbon, which has zero effect on the toe resistance. When we dig into the result, the issue was interpretation of the test. What you see in the figure in the right is, sorry, let's start with the left. What you see in the figure on the left is a typical squid test result in soil. And then you have threshold that defines the beginning and end of the sediments. And those were used in the interpretation I showed you before. What you see in the right is a typical test result in the rock. And you can see the difference in the pattern. Here is another example of rocks. This is not Gordie Howe project, it's a different project. Here is the result of the squid test in a rock socket before it was cleaned properly, or it was clean and then this was the result, and it was cleaned again, and then you can see the results. It was completely different. Here is the test results on the Canadian side and the test result on the US side. Therefore, this thickness of the sediment that we saw, and it implies they are the same, they're actually very different. Hence, we have to be careful that the conventional values to interpret the squid test so far in the industry is more tuned for the bedrock, so more tuned for the soil, not for the bedrock, and some adjustment is required to get consistent results. And as I mentioned, we're going to talk about a little bit about dry drilling method. Dry drilling method is some contractors use. It involves drilling your drill pile into the wet non-plastic soil, like silt, sandy silt, silty sand, and they create a plug, maybe 2 meter, 3 meter plug even, and they keep the steel casing 2-3 meter below the plug until they reach the toe, and they think everything's fine because they don't see any problem. What you see in here is the lines are the SPT values before a construction was done, and practically the yellow is the bound of the SPT values in the original ground. And then we went and advanced boreholes over around here is 15 piles, something between 300 millimeter to 600 millimeter away from the edge of the piles. This is not even representing what's happening right at the edge. And The green represent the SPT after it was drilled. This construction was done without any red flag. Everything seems okay, but it was a dry drilling method in a very dense material. And as you can see, the SPTs drop 2 feet away from the shaft. Therefore, you don't have the same soil that you think you have. And the effect on the base was even much more severe. Uh, that's the pilot test result. You can see that actually at the beginning there is some softening, and by the time the base settles 60 millimeter, it start stiffening up because the disturbed zone under the load now is being compacted and becomes stiffer. Here is a few pitfalls about using the pile load test for the drill piles. I mentioned the O-cell test. I'm going to provide a little bit of background, a high-level overview of the O-cell test. Is the practical way of testing drill piles. It involves installing a jack at the middle of the pile and then applying load upward to the above the jack and downward below the jack. You apply it upward to the top of the jack. Obviously, it's mobilized shaft friction in here. You apply the load below the jack, it mobilized shaft friction upward in here and the end bearing in here. And it's a very cheap, very effective test for the drill piles. Generally, in the case of the rock socket, this jack is at the bottom because you want to put the load, jack at the location that the load in the top and the bottom fail at the same time. Now, in order to investigate and research some of the items that I'm going to discuss with you, we wanted to run FEM models, but we had to make sure that these FEM models are, for the lack of practical word, perfect or perfect for the purpose. As you know, you cannot find an element modeling of a pile and you get the load displacement at the top properly done, but it doesn't give you proper load distribution with the depth or mobilized shear friction at different load levels. The model should be as accurate as it can get to be relied upon for a generalized research. Therefore, what we did for this particular test in soil, this is just a proof that we get very good match with the load distribution with depth at different load levels. Same as the load displacement upward and downward, and also mobilized shaft friction at different levels. This was one of the tests that we used. This one is in Gordie Howe. Again, that's the upward movement and the mobilized load from the test versus the modeling. And here at the base, good match. And then we use all of that to study how we're going to use the test result for the actual pile. First thing, intention. That's the more common mistake I have seen some folks do is they think if you get an ultimate shaft friction from the O-cell test, you can directly use it as a tension resistance. Why they think that way? Because they're saying when you do the O-cell test, the mobilized shaft friction is downward. Therefore, that's like a pile being under tension. Hence, we can use the result as is. Whatever ultimate shaft friction we get from the O-cell test, we can use it for tensile resistance. That's actually not correct for a simple reason. When you do the O-cell test, this is the load that applied to the pile. And as you can see, the pile still is under compression. And due to the Poston effect, this pile is being horizontally expanded. And if you recall, we talked about the of roughness. Therefore, horizontal expansion affect the normal stress, and the roughness comes into the effect. Versus in tension, tensile loading, the pile itself is under tension, and then you have horizontally reduction of the cross section. Therefore, you have reduction of the normal stress on the shaft, and both of them happen despite that the mobilized shaft friction is downward. We use those calibrated model that we show you. Here is the result. We get the ultimate shaft friction of 115 meganewton from the O-cell test in the rock. And when we simulate the same test with identical result and everything the same to simulate a real tension, the ultimate tensile resistance is 45% less. Therefore, if we were going to use the O-cell test for the designing the tension, we should have used 45% less value. Same thing for soil. In this case, the percentage is 70%, therefore less reduction as expected, but it still is not the same. Another issue that come to the effect is conducting an O-cell test for a certain length. Let's say you have 3 or 4 meter rock socket and you do the test, and then suddenly you want to use that to design a 6 meter rock socket. Generally, when we do the O-cell test, we try to put instruments like strain gauges within the test to provide us axial load, and from there we get average mobilized shaft friction at different zones. And this is a sample, like this is the average friction for the entire rock socket, and then for the lower zone you get this value, for this upper zone you get these values. And what some folks do is when they want to increase the design to production pile, they just assume whatever was the highest value in here for this lower zone, like 4.49, and just apply that to come up with a longer length for the production pile. This approach is unconservative for this simple reason. In the O-cell test, you have load applied upward in compression. Here you have higher axial load. Here you have lower axial load. Hence, here you have more lateral compression. Therefore, confining is more at the bottom. Plus, you generally have better rock quality at the bottom. Therefore, two items come together to higher confining, better rock quality to give you the total mobilized load in here versus, and you have increased shaft friction versus in the real top-down loading in the real piles, you have higher confinement at the top and generally lower rock quality in the top, becoming better with depth. Hence, if you have a slight deviation between the actual production pile and the O-cell test, yes, you can use the result as is. But if you're gonna go and have a large difference, then you better pay attention to these possible changes in the rock socket. Another thing that you have to generally consider is most of the time the rock socket are actually not behaving like a deep foundations. The depth to diameter ratio is not close to 5. All of that come to the effect in interpreting the test results. Another angle is coming back to the need for base cleaning. Even if you're designing the purely shaft friction piles, you're not relying on the end bearing. Still, the base resistance have some effect because when the base provides some resistance, your shaft friction is even increasing. Like here, we simulated a scenario that there is a void at the base, and where there is a soft base, and as you can see, there's 20% difference between the ultimate shaft friction because base providing some resistance increase the lateral confinement, increase your shaft friction. At the end, what I appreciate if everybody learns from this is construction means and method and workmanship has profound effect on the geotechnical resistant casting place piles. It's not just about the geotechnical property of the soil or the rock. These two come to the effect together. As a designer, particularly for the large bridges with the heavy loads and sensitive foundation, you need to have a clear understanding of construction methodologies. Your design must be very consistent with the construction specification. Issues like, can you have a permanent casing? Whether the permanent casing can have overcut? How does it affect your shaft friction, lateral, axial? Quality control, it's one of the most important items. and you have to pay a special attention to interpretation of pilot test, particularly if you deviate a lot from the parameters of the pilot test, whether it's diameter or length between the pilot test and the production piles. Thank you for all of your attention. I think we have some time for the questions, Leonardo.
This is great. Thank you so much. Really appreciate your presentation, Masoud. Wow, what a size of foundation. This was incredible just to hear about it. Thank you. Um, well, we do have two questions already prepared here. I'm gonna read the first one. It's from Sam. They're asking to assess the interface friction between the rock and the concrete. Did you consider doing direct shear test instead of triaxial? If yes, any practical or technical reasons to choose triaxial test?
Actually, I have to say, Sam, the interface test. Let me see if I can get back in here. The interface test was direct shear test. I'm going fast to find it. Here, okay, it was a direct shear test. We cut the core in a vertical line. We cast cylinder, and then it was a direct shear test. Of course, I have to rotate it vertically to show the orientation of the sample versus concrete. But as you can see, this is a direct shear test apparatus. This line is practically this line. Therefore, it was a direct shear test. We did the triaxial test for the intact rock and some of them for the natural joints, plus lots of direct shear tests on the natural joints.
Thank you for answering. More questions are coming. We probably won't have time for all of them. So if you are a young professional, please feel free to type them, and all the questions that will be unanswered during this last 12 minutes that we have, we will be replying over email. So the second question here is from the Denial. What method did you use to approximate the pile compression and tension capacity for the design prior to the load tests? And what methods did you use to calculate the spring values for designing the pile caps?
Oh, very good question. Going back to the slides, of course, I'm not going to shoot through it now. For Gordie Howe test, which was a very large bridge, we used all the tools. We used anything from empirical test methods to calculate the capacity, and then verify that by running numerical modeling of the rock socket, as I show on the slides. Uh, those were very important to get there. And then we verify that by the pilot test. And of course, I think I mentioned that that's not something you do for every job or even every large bridge job, but that was an exceptional project. It's required that for the other piles like the Portland bridges, we just use the empirical method, but we know by experience, like in that rock formation, what method works best, plus the previous experience in the local geology. We used that, and then all of that was verified by the pilot test. So now, do we have time for another question?
Yes. So question from Mohammed. Can you please elaborate on the issue with the dry construction method and impact on side and end bearing resistance?
What will happen in the dry construction method is, again, this is comes into the effect when we have non-plastic soil like sand, silt, underground water table. Is as you excavate and you go down, you have a difference between hydraulic gradients between outside and inside your shaft. Now, you don't see water gushing in because you have a plug, but these hydraulic gradients try and, sorry, let me get to that slide too. Try have a tendency to bring the soil into the shaft because there's a hydraulic gradient. You cut this and you remove it as you go down. Therefore, you don't see or you don't get a feel for what is happening. Uh, but the tendency to come in is already start disturbing the soil even beyond the edge of the pile. And then by the time you get to the toe, at the design toe, you have no plug. You have zero plug because the steel casing doesn't go below the design toe. Therefore, that's where you get the maximum reduction in the soil and disturbance, and then it affects your soil properties a lot. And as I show in here, like generally in every pilot test, if things done properly, you see a little bit of hard behavior that becomes softer. Like that's the type of behavior you like to see. In this case, we have enough disturbance that is actually softer and is becoming harder because you're compacting the soil. You're compacting the soil that disturbed. If you look at FHWA guideline for the drill shaft, plug method or dry drilling method is not even one of the acceptable method in non-plastic wet soils.
Next question is, do you have any suggestions for frequent groundwater table variations on shaft resistance?
I'm not sure how frequent like variation you're talking about. In most of the projects I were dealing with, groundwater table variation has been 1 to 2 meter, like seasonal fluctuation. That, and then you consider the highest one in your analysis, of course. When you do the pilot test, you can have some reduction because your effective stress reduces. That doesn't seems to me a big deal to just incorporate in your whether back calculation of the pilot test or in your design process. You just need to know what is the variation of the groundwater table over the lifetime.
Next question, would you revise the shaft and tip resistance discussions if the CIP is socketed in shale?
I don't revise the discussion because one of the examples I show you for the Portland project is all in the Georgian Bay Formation. They're all in shale with the limestone seams. One thing I can add, it wasn't in the presentation, is some rocks like shale are more susceptible to weathering. Therefore, if there is a big time lag between the construction, augering the rock socket and placing the concrete, you may have some deterioration of the rock, which affect potentially your shaft friction. Generally, what I personally do, I make sure that the contractor simulate the longest time lag in the pilot test. The production pile having a smaller time lag, therefore you know that you capture the worst case scenario in the pilot test. But at the end, some of the red flags are there, like in the case of toe resistance, as I mentioned. When you do a pilot test in shale, you better have a borehole at the exact, or I mean, not the exact location, right beside your pilot test to make sure that you're not installing your pilot test very close to a limestone seam and getting very, very high results that are not representative of all of your production piles, because your production pile may not be 6 inch above a limestone seam. Therefore, try not to do a pilot test without having a representative borehole for the pilot test location. Otherwise, the interpretation could be tricky in a situation like shale.
Next question, was there any indication of developed residual loads in the piles due to construction and concrete curing? And if yes, were they taken into consideration during interpretation of the results?
Uh, Very good question. There are some because there are strain gauges inside, and as I mentioned in one of the projects, actually in two projects, we even put a load cell horizontally to see the residual horizontal locked in horizontal stress at the end of the concrete curing. Uh, Therefore, they are there and they become part of the interpretation which the pilot test agency provide at the end. but it was not significant. On the axial side, it was not significant.
One question here found interesting from Reza. Can you please elaborate on pile group efficiency? Did you consider full capacity for a singular pile, and were the piles sufficiently spaced?
Of course, the answer is yes. On the axial capacity, um, uh, in the projects that I mentioned, I show it to you. There was no reduction on the toe resistance on the ULS side, and then there is a softening, meaning you get more deformation on the same load because you have the group effect. Therefore, if every pile is loaded to the same level, now you have a little bit of more settlement because you have bigger bulb, a stress bulb. On the lateral of, I mean, that's a very well known. On the lateral resistance, there is a big group effect that you have to consider.
Next question. As described for the lithology foundation, below the fill soil, a thick, very soft clay at 21 meters. Is there any soil improvement or surcharging has been implemented to improve the clay mechanical properties?
No, that was not part of the plan. It's on the axial side, whether tension or compression, it was all about the rock socket behavior. And on the lateral side, we used whatever we had. I mean, whatever resistance we could get from those weak soil, and it all worked out. We didn't need to do soil improvement. And remember, in that case, on the axial side, your soft clay eventually may lead to down drag or negative skin friction that you have to consider in the design.
Perfect. We'll have time for one more question. Is there one specifically you'd like to answer, Masoud?
Oh, no, I wasn't reading them. Please, Leonardo, choose one.
Of course. So there's one question here for the shear friction assessment between the concrete and the rock. Is this the first time I hear that can be tested by direct shear test with this interface? Is there a standard ASTM test or is something that you developed specifically for this project?
No, this is something we developed for this project, using a few other projects. It was a good indication. Again, you shouldn't expect to get the same thing for so many reasons. Uh, One of them is we do a socket is the lower bound of roughness. Your actual rock socket will have rougher, which means is a better. But at the same time, the quality of concrete is not the same in the rock socket versus what you do in the lab. That's it going in the other way. Uh, for us, it was a good indication in one sense. You know that the empirical method of establishing shaft friction, there's so many different equations with different research. They give you a sometimes very wide band of results and help you to fine tune which way you could go. Uh, or at least you know that if the contractor doesn't do any mistakes and the construction is proper, what level of result you can get. Uh, I know if the test gives you 2 MPa, proper construction may give you 1.8, 2.2, or something like that. But if the test gives you 2 MPa and you suddenly get half an MPa, you know that something went wrong in the construction. But this is no, there's no ASTM. It's all new because there's lots of issues with this test for interpretation of it into the real result. I mean, I can point several issues myself, but it is the best we can do for an important job to get some idea.
That's great. Yeah. Well, thank you so much, Masoud, for answering all these questions and for the presentation, for being here. We're really, really grateful for your presence. Also, thanks to everyone who participated in the questions. If you have any unanswered questions, please feel free to send them over to the email that I type in the Q&A. It's cgs.yp.committee@gmail.com. We will be gathering those questions and sending them to Masoud to answer them.
Thank you, Leonardo. And again, thank you everyone for attending. Thank you, young professional, for organizing it. I hope I could successfully share some of my experience with the young colleagues.
You surely did. Thank you very much.
Thank you.
Just one additional note. We have another webinar coming up next week. It's a non-technical webinar about geotechnical encounters with Lucy Phillip from Stantec. So stay tuned to our LinkedIn group to find the link. And thanks everyone. See you next week. Thank you,
Thank you.
Masoud.
Have a great day, everyone. Bye bye.